it is my great pleasure to introduce Professor Anderson S.L. Gomes. Professor Anderson Stevens Leonidas Gomes, a distinguished physicist, was born in Recife, Pernambuco, Brazil. He embarked on his academic journey at Physics Department of the Universidade Federal of Pernambuco, culminating in his graduation in 1978 and a master's degree in 1982, both in physics. Driven by a passion for laser physics, he pursued his doctorate at the Imperial College of Science, Technology, and Medicine in 1986, followed by postdoctoral research at Brown University in the USA in 1992. Currently serving as a professor of physics at the Universidade uh, Federal Pernambuco. Professor Anderson specializes in the laser applications in nano and biophotonics, nonlinear optics, and nonlinear photonic devices. His significant contributions to the field are evident in his impressive portfolio of over 300 scientific publications, with a notable H-index of 48 on Google Scholar and 36 on Web of Science. His impact on the scientific community is substantial. Beyond his research, Professor Anderson is dedicated to nurturing future scientists, having supervised 39 master's dissertations and 20 doctoral theses. Recognized for his academic excellence, he holds a prestigious CNPq fellowship at level 1A. As a fellow of Optica, he served as the president of the International Council from 2011 to 2012. Professor Anderson is a distinguished member of the Brazilian Academy of Sciences and holds the position of regional vice president for the northeast of Brazil. His affiliations extend to the World Academy of Sciences, the Brazilian Physics Society, and the Brazilian Society for the Advancement of Science. In acknowledgement of his outstanding contributions, he has been honored with the National Order of Scientific Merit in 2010. He received the Commander class in the area of physical sciences, a presidential award, and achieved the class Grand Crux in July 2023. His commitment to the advancements in scientific knowledge and inspiring the next generation of physicists continues to leave an indelible mark on the world of physics. On behalf of all the RIOS members, I welcome you, Professor Anderson, to this webinar, and I also welcome all the invited guests and the participants to the webinar. Now I kindly request Professor Anderson Gomes to begin the presentation.
Let's start then. I'll be talking about the Raman solitons and Raman random fiber lasers. This is where I come from. So this is South America, and then we have Recife is right here. So at the moment I'm in a city around here. It's Salvador. So Recife is a coastal city, very nice beach. This is the main part of the old city center, and all of you are welcome to visit us. This is our campus. It's a very comprehensive campus, and the physics department has about 45 faculty members in different areas of research, and the optics research has about 12 members in different areas of knowledge within optics. Our group at the Laboratory of Photonics and Biophotonics, we have a very good group. As I am also in the dentistry program, so we have a group with physicists and dentistry. A lot of international and national collaborators. Perhaps you know Paras Prasad and Raman Kashyap, that we have through them a lot of collaboration and have visited India many times. So today we are going to talk about Raman scattering, and this is of course a very well known and well established subject. We know that when we have light interact with matter, many things can happen. Of course, depends on the intensity of light, but even for low intensity, we have the scattering of light in the medium in general. This can be very weak scattering, but can be strong scattering. And if we look on a more scientific point of view, if we have incident light on a microscope or molecular atomic level, we know that there are absorption. So the light can be absorbed, can be fluorescence, can be different things happening. But here we are interested in the scattering of light. So this is a virtual level, so there is no level. So the scattering is such that you can have scattering coming, light coming back or forward or sideways at the same wavelength. But if we excite some vibrational levels, then you can have lights at different color. And the difference in the color comes exactly from the difference in energy that was found out many years ago by Raman, and nowadays it's the Stokes emission or anti-Stokes emission. And then this is the so-called Raman scattering, as we know. And this molecular level can be of any material, and is actually a fingerprint of that material. So this is, without putting any equation, which are well known, this is how the light scattering happens. The Rayleigh scattering discovered by Lord Rayleigh, and then the Raman scattering in both sides of the spectrum. And nowadays we know that we have from using Raman scattering as a diagnostic tool for all kinds of light matter interaction, chemical applications, biological applications, imaging, but we can also use these as light source. And that's what I'm going to be more discussing more today, or remind you of some of the what's in the literature about Raman scattering as a sort of light. So many landmarks and many historical and special numbers have been dedicated to the Raman effect. We know that in practice, a typical laboratory setup requires a laser to have the sample at some position. The light that comes back is then analyzed in a spectrometer, and you can then make all the signature of the material. Nowadays, you have a very fancy, commercially available Raman spectrometer. They can be this size, or can be even kind of hand size, that you can do it basically in situ experiments. So I had the opportunity to visit India, as I said many times, and one of the times I went to Calcutta, where I gave a talk. It's called the Hair Professorship Lecture. I was invited by Professor Amitabh Patra, who is now in Chandigarh, and of course I had the opportunity to see the first Raman spectrum that was used in 1928, and this was one of a very excited visit, and of course this is me here, properly dressed. Okay, so today and from now on, I'm going to talk about mainly glass, silicon dioxide. We know glass can come in crystalline form or amorphous form. I'm more interested in the amorphous form. The Raman spectrum of crystalline silicon dioxide has very sharp lines, which the known Raman shifts, some of them very intense, in this case about 490 nanometers, wave numbers from the pump. So you excite at some wavelengths, and then 500 wave numbers later comes this peak. In frequency or in wavelengths, this emission depends upon the wavelengths that you are using as the incident wavelengths. In the case of the amorphous silica, the spectrum is very different. It's typical of amorphous material, but again, you can identify all the bands which comes from the silica dioxide moving different ways, and this is well understood nowadays. And this band is what we're going to exploit from now on. And we want to exploit this in an optical fiber. So optical fiber is a well-known device. It's a passive device. You have light, the light transmission optical fiber. We learned this very early in our life. It's due to the internal reflection, total internal reflection. Light comes into the core of the fiber, which has a refractive index a little bit higher than the the cladding, and so light is trapped and can travel. Nowadays, you can have traveling for tens of kilometers with very low loss. We have a single mode fiber. Typical core is about 9 microns, nucleus about 125 microns. Can also have multi-mode. And here, again, we are concerned mainly, we're going to exploit more single mode fibers. We can have bundles of fiber, cables of fiber. It's responsible for allowing us to be with you, because light, all what I'm talking about here is flying not only through air, but also through optical fibers. So there are many early papers and recent papers even on stimulated Raman scattering. Stimulated because normally when we see this spectrum here, where we have the relative Raman gain, it's so-called spontaneous Raman gain. We excite and we look at the spontaneous emission. Now, if that can propagate or can be amplified, the amplified spontaneous emission can become very narrow, if you work properly with it, so you can use it as a source of incoherent light, but it can be made a laser and then can be exploited, as I'll show you some examples. This is a typical experimental setup, laser, fiber, and then go to spectrometer. And at that time, I'm talking about the 80s, normally we use the boxcar rather than more fancy equipment. In this case, two types of lasers were used. One mode-locked, delivering short pulse at 514 nanometers, argon laser. And this is a Q-switch frequency double neodymium laser. So typically, what you see in this spectrum here is in this figure here is the spectrum showing one of the Raman peaks. And as you go up in power, you can see the second peak here. This is the input power in this other figure here. And then the peak Raman intensity, arbitrary units, but show that this is one peak and the second peak, 440. So you can have these characterized to use as light source, if you like. You can also, besides looking at the first Stokes, you can look at the second Stokes. That means the process is happening twice because the intensity of the first Stokes is high enough to excite the second Stokes. So this is, again, from there, nowadays we know that it can be the base together with other nonlinear effects fiber to continue light generation. So you can start with several picosecond pulse and generate continuum in a fiber where we exploit stimulated Raman scattering, self-phase modulation, four-wave mixing, other effects in optical fiber to generate a tunable light source, if you like. So since the 80s, after the pioneer work, many great developments, many things, and this is a typical device that we can have nowadays for a Raman fiber laser. So this is a diode pumping at 1455 nanometer. Here, this is a fiber that we want to exploit the Raman scattering. There are two mirrors here, and those mirrors are inscribed in the fiber as a fiber Bragg gradient. So it's a very compact device. This is a paper from 2010, but you can see here you have the Raman band, and then this is the laser emission on the top, riding on the top. This is the emitted power, intracavity Stokes. You see you can have for, say, 1 watt, 300 milliwatts, it's a very efficient process. And this is a typical line weight you see as it's lasing. This is this line here, a few nanometers, much shorter than the spontaneous emission. So nowadays you can buy this kind of laser. It can be very high power, very high intensity, lots of fancy things that can be done. This is now a commercially available light source. You can look at some of the recent books for a review. I will not have time to go through all of these achievements. So I want to mention some of the early work I did at Imperial College during my PhD, and this is on solitons. So when you have an optical fiber, several other medium, light propagation is described by the so-called nonlinear Schrödinger equation. This is an equation that is easy to interpret. A is the amplitude of the wave that's going to propagate along the ZX, so along the fiber. This term here is related to the group velocity dispersion. So light, a pulse of light propagating to a medium with a refractive index, it tends to broaden because of the dispersion of the material. And this second term here is the nonlinear response of the material. As you can see in fiber, this can have a sign here that's negative or can be positive, and the other one is negative or positive. In fiber, in glass, for most of the wavelengths that we use in the visible and near infrared, the nonlinearity is always positive, but you can modify the fiber to work in the so-called negative group velocity dispersion. So if you do that, what happens then is this equation, these two terms here can be balanced. So if this one, the second compensates the third, this equation is going to be just the amplitude equals to 0. That means the light that you put in, of course I'm neglecting loss, it's going to propagate without distortion. That is no linearity and no dispersion affecting. They actually are there, but they balance each other. So this, for this so-called n equal 1, and there is a, you can write there, you can work out the equation and come to this number here, which depends on the intensity, the pulse duration, the nonlinear parameter, and the dispersion. So if you play those numbers, you can calculate the intensity for n equal 1, then you can have a pulse propagating in principle forever. We know loss is going to affect at some point. You can have second and third order solitons. So the first experimental observation of this was done in the 1980, and then this is the soliton, the fundamental, the second order, and so on. But it is well known again. And at the same time, in the 80s, we were working on this, but we were exploiting the Raman generation of the fiber to generate optical solitons. In a recent paper by Roy Taylor, who was my supervisor, is a professor at Imperial College, he wrote very recently a review on early optical soliton research at Imperial College. And this is for those that are interested in, a little bit of history and want to know what happened at the beginning of all this research, can look at this paper. But just a couple of examples. So this is one of the architectures that we provided. There we had a CW mode-locked laser generating 100 picosecond pulse, and then we made this cavity. So we could work, just the light would go through the fiber, and then we could measure everything here, so single pass, or we could put those mirrors and make this ring cavity. So the result on the right-hand side here is showing the measurement here in a single pass. It starts from here, where the laser point is. You can see there is a peak here, which is the laser, and two side bands. This is spectrum, wavelengths. So these are two side bands. These are due to four-wave mixing and actually lead to what's called modulation stability. Now, as we increase the power, so power is increasing from bottom to top, you look at this band here, it starts to broaden, and that's due to the Raman scattering. So you start to broaden, and you broaden even more as you propagate until you generate a quasi-continuum that goes from 1.3 to 1.5. Now, if I look at this band, it supports what we call soliton-like compression. So as it broadens, it propagates, the intensity is getting up, and it generates solitons. And when we measure the pulse that comes, we start with 100 picosecond, and we have about 100 picosecond. There is a background here, which is not shown, but it could be cleaned up, and then we generate femtosecond pulse in a single pass. So now, if we now take this off and look at the cavity, this is spectrum without cavity, and when we put the cavity, now the cavity somewhat selects, and you have a Raman like here, and in this you also have a soliton formation, and you have a femtosecond pulse. So we did a lot of different work, just playing with the fiber to generate first, second, third order solitons, first, second Stokes. We could do all kind of tricks And as I said, this is all reviewed in this paper, and there is also a book on optical solitons by Roy Taylor. So now let's go to a modern. So this I was talking about, late 80s, beginning of the 90s. So then I finished my PhD. I came back to Brazil at that time, and in the last several years in our lab, we have been working with. Now it's not a new kind of laser, but it's a different kind of laser mechanism. We call it a random laser, and then of course a random fiber laser. So what we know that a conventional laser, it has a medium, the two mirrors, pump source, optical cavity. Fiber laser, as I just showed you, can have two mirrors, or you can have the two fibers, as I again shown you in the few slides ago. Now, what I'm going to explain to you, and to maybe some of you know, or it's what we call a random laser. So you pump some gain medium, let's say a dye, and within this dye, we put scatters, like titanium dioxide. So light is going to bounce in this scattering, like it bounces in the molecule, and then it returns to the medium, and then it provides optical feedback. So in a conventional mirror laser, the optical feedback is along this X, and you have a coherent emission spatially. Here, optical feedback comes from all over. So you have emission to all over the place, but this emission is coherent. It has low coherence, as I will mention later, but it's a coherent emission. It's actual laser emission. Same thing can be done in a fiber. You can use different kinds of fiber, conventional fiber or microstructured fiber. You can pump longitudinally, or you can pump transversally, and you can look at the emitted light. And again, you don't have mirrors, and this is even cut in an angle to avoid the reflection, the 4% reflection from the fiber. So the pioneer work for what we call today random laser was proposed by Vladimir Letokov back in '68. It was a theoretical paper. There are a couple of papers in between '68 and '94, but our publication in '94 demonstrated in a very definite way that you can have laser action in strong scattering media. Then another paper by Hui Shao showed this in a semiconductor powder. And in 2007, we demonstrated the first random fiber laser. So this is a talk on itself. There are many, many things that happen. For you to have an idea, this is the timeline that goes from, if you see after 94, after our paper, you can have a random laser and random fiber laser in most of the materials that you can think about. You can have cold atom, colloids, DNA. You can exploit plasmonic effects, polymers, all kinds of things. Even in our skin, you can have it in a flexible way, in optical fiber and so on, and applications. So by a simple definition, a random laser is an optical source where optical feedback comes from light scattering in a disordered medium. So it can be scatterers inside the gain medium, so like titanium dioxide or even metallic nanoparticles in a dye medium or a polymeric medium. The scatter can form the gain itself. So if this is, say, a quantum dot or zinc oxide or rare earth, you can have it lays and it scatters. So you can do this in a colloidal, as a colloid, as a powder. You can put this in a membrane, on a chip, and then optical fibers. And I'll be more discussing optical fibers today. But this is very general about random laser. They are mirrorless, but they are not loadless. The modes of the laser, as we know, it comes from the cavity. Although we don't have cavity in our case, but we have the optical feedback, and the optical feedback provides the modes. So to be a laser, it needs to have modes, and that's what we have. It's actually a multi-mode laser. So there is the spectrum is independent of the resonator frequency, because there is no resonator, as we know. There's not a fixed cavity. As you know, the resonator frequency does not depend of the gain medium. If you have an empty cavity, you can have the resonance frequency. So the tunability and directionality can be managed. And for those that are more experts, if you want to prove that the source is coherent, you have to do the photon statistic, and it should be Poissonian rather than those condensation, those statistics, such that, and in this case, there are several demonstrations that random laser, the statistics is Poissonian. Now, people have already studied all kinds of properties, threshold, pump volume, particle density, and so on, tunability control techniques, directionality, spatial and temporal coherence, polarization powers. Everything that you can do in a conventional laser has been developed for laser. So we have a publication in 2021, which is the most recent review on this subject, that is very comprehensive. It has from theoretical background to applications that I'll briefly mention some of them here. So just to remind, I think I still have some time, at least about 15 minutes. So the very first paper, as I said, what we did, we have a frequency double the egg. This is the cell, and we pump the geometry to avoid any reflection. So there is no reflection here. So this picture here shows the broadband emission from the amplified spontaneous emission or all spontaneous emission from the dye. Now, when we put nanoparticles within this cuvette, these are titanium dioxide, so dielectric nanoparticles, 250 nanometers. What we see now is this very narrow peak, which is lasing at these wavelengths, and actually at this wavelength. This is the line weights reduction you see here, and this is the threshold curve. So you have the threshold here, which is about where the line weights collapsed. That was a very first unambiguous demonstration. And as I said, since then, lots of work have been done. And I'd like to point out this work in 2014, where this group here, it's a collaboration paper, they exploited powders like barium sulfide. This kind of powders, they are what we call Raman active. They have a very intense Raman emission. And what they did is they pumped, as they pumped, each of those powder is scattered, and then excited the next and excited the next. So this collectively, this is the emission from the powder, pumping at 532 nanometer. And look, 1,000 wave number later, it's more towards the yellow, and you see they have seen the two Raman lines from this. And this was a very interesting paper, again, using the Raman effect in powders. So I'm going to talk now about random fiber laser. The first random fiber laser that we developed, it was based on a microstructure fiber. It had the dye inside, like the cell. We pumped transversely and look at the emission. You see now we have a very handheld spectrometer, and you see the line weights reduction here from low power to high power. So this is the line weights reduction for 24 nanometer to less than 5. This is with scatterers, and this is without scatter. You see there's no line weight reduction. And the blue curve here corresponds to this situation, no powder, no scatters. Now with scattered, you see a clear threshold and the power emission, both total power or peak power, because this was a post laser. So after this work in 2007, Raman Kashyap and his group developed this fiber Bragg grating based random fiber laser. But this fiber Bragg grating, they were not fixed. The fiber Bragg grating, it was random fiber Bragg grating. That made the whole difference. But for what I'm going to discuss here, I'm going to show some examples of using Raman scattering as the gain medium and Rayleigh scattering as the scattering feedback mechanism. So this is the paper by Sergei Turitz and his group in the UK. What they did is they got a very long fiber, 80 kilometers of fiber, with a Raman gain that was distributed along the fiber. They pumped in two ways, and what happened is drawn in this this cartoon here. So as they pump, they get scattering due to the Rayleigh scattering. Rayleigh scattering fiber is very, very small, but integrated along 80 kilometers, it becomes strong. So the random feedback came from Rayleigh scattering. They had 2 pump lasers, and then after some power, which is shown here, is very small, but it's about 1.5 watts power. You see the threshold, random laser emission. This is the spectrum of the Raman emission in the glass that you already saw. And this is the Raman emission here. This is what it's going to laser. This is a very high power. You see a very clean, and those 2 lines here, they become these and these, which is the signature of the random laser at this wavelength. So this is reviewed. This is a 2009 paper, so it has some review in 2014. So this was the first one. Nowadays, we have a random laser in the way I showed, using microstructure fiber, but the more practical ones are those 2 where you can use rare earth doped ions in fiber grating that are randomly distributed. So this is a conventional fiber, erbium doped fiber or neodymium doped fiber. And here we have the Raman or Brillouin as the gain medium, and the Rayleigh scattering as the scattering process. So here are some examples from the group. You can pump forward, backward. You can have single pump. You can have a half a mirror. You can have all kinds of architecture. For instance, the forward pump scheme is good for low threshold. These are some examples from the group of Zinan Wang in China. So this is a pump at 1365 nanometer, conventional fiber here, 94 kilometers, and they can have, they can play, and then with more than 50 kilometers, you can even have third order Stokes operating. So this curve here is very interesting. As you increase, have the first order, the power is high enough to start generating the second, and then it's consumed. This power is, all power here is taken to this one, it grows, and then it saturates. When it saturates and drops, it's because the next Stokes coming. So it can be, nowadays you can have up to 5, 6 Stokes. So that means you can have a tunable source in the near infrared. You can also use short fiber lengths. By short, I mean a few kilometers, 2 or 3 kilometers. In this case, it's 1 kilometer fiber. So everything else is the same. The idea is the same, and they have what's called half open cavity. You can be clever and exploit a different kind of pump, and then you can have tunability. So those 2 figures here, this is the tunable pump laser. So as you tune, the Raman is going to be automatically tuned. So this pump laser here is based on ytterbium doped fiber, and then you have 10 kilometers of special fiber, and then you can see different Raman lines here as you pump. So different Raman lines because you are tuning your pump laser, and then you can have a 300 nanometers continuous tuning. Okay, you can also have a nowadays you have over kilowatt power CW, continuous wave, random fiber laser. This is again work from Zinan Wang group, and in this case, that is from 2019. They obtained almost 1 kilowatt in the first Stokes, as you can see here. So lots of development on this side, but I'd like to next 5 minutes or so to allow time for questions. I'd like to just not change a little bit to show you what you can do with those kinds of lasers. This cartoon here, it shows the laser, the random fiber laser, using an erbium doped fiber. It's a fiber that you can buy commercially, but in this fiber, there is a random phase fiber backgrading that was inscribed on it. So these act as scattering, random scattering, because the scattering means fluctuation in refractive index, and that's what it's done here. So if you pump this, you can have a random laser emission, and we have exploited this random laser emission to study what we call complex photonics. We can see by analogy many things that people study in magnetism, statistical physics, complex system. For instance, transition from paramagnetic phase to spin glass phase. Something called Levy flights. I'm going to give you this example. Transitions from ferromagnetic phase to spin glass phase. Extreme events, turbulence. You can also see Bose-Einstein condensation and the photonic Hall effect. So these are all by analogy with things that we know from other areas of science or physics, or even complex systems like turbulence. So as an example, this is some work that we did not long time ago in 2019 together with the Chinese group. You know about a random walk, right? When you do a random walk is explained at the end by, in the so-called central limit theorem, by a Gaussian distribution. However, if you have these walks that instead of being localized in this way around some place, they can do a little bit of Gaussian random walk here, but they can go long flight and then another long flight. This is done by birds. Birds searching for food. That's what they do when they are, those flights that you certainly see. In this case, this is described by a exponential tail-like formulation, which is called Levy statistics. So it's a different statistic than the Gaussian one. This Levy statistic, I'm not going to go into details on the equations, but just to point out that this alpha, this number here, is goes into this probability distribution, and this is a number that if it's between it's 0 to this parameter governs it governs the strength of the fluctuation. So what we are going to do is look when we get the spectrum like this. We are interested not only in the spectrum, but what happens with the fluctuation of the intensity. I'll show you this in more detail. So this fluctuation here, this number alpha, if it is between 0 and 2, the statistic is governed by Levy flight, or if it's equal to, it's a Gaussian behavior. So what we do, we provide a random laser. In this case, we pump at 1455. This is a 5-kilometer fiber. We have a mirror here. So this is a half open cavity laser. And then we make the analysis. So this is the Raman emission, spontaneous, below threshold. This is around threshold, and this is above threshold. You see it's a clean because now it's laser. So what we do, we take a lot of these, like thousands of these spectrum, and apply the statistics for here. And then this is what we call, we can look at the average. The probability can be like this for below threshold, but if it's above threshold or around threshold, you see it has this exponential tail. So if we plot that alpha parameter, that's an indication of the so-called Levy indicator, you see this is the threshold. The threshold of the laser is here. This is normalized, this power normalizes the threshold. Threshold starts to go up. So the statistic is 2, and then comes to, it should go to 0, but it goes here all the way down, and then it recovers to 2 again. So this kind of plot is a typical signature of the so-called Levy spectral intensity. So besides, now we use this kind of random laser using the erbium. So the other one, this one here, was using Raman random fiber laser. But for this one, which I'm closing my talk with this, we have a 30 centimeter only erbium fiber laser with a random break grading. So this is, in this case, erbium. So this is the spectrum below threshold, above threshold. And then we use these to do the same kind of measurement. So this is Levy statistics. So you see that's alpha. Here it's 2, goes to almost 0, and then comes back. It's a more interesting, clean result, if you like. And this is the signature of another phenomenon called replica symmetry breaking, which has to do with the transition from paramagnetic to spin glass. Now, we have observed this transition that's called glassy behavior in that fiber, Levy statistics, extreme value statistics. And you remember in 2021, the Nobel Prize in Physics was given by two persons on climate change, and this guy called George Parisi for his discovery of the interplay of disorder and fluctuation in physical systems. So what he did, it's describing this scientific background paper, and the evidence of the so-called replica symmetry break, this Parisi theory that gave rise, allowed him to get the Nobel Prize, was first observed in random lasers by a group in Italy. This is this reference 30. Then we did a lot of work on that, and the most important thing, which I'd like to point out here, is looking at from my personal view, is that the nature of random laser allowed for the concomitant observation of replica symmetry breaking, which was Parisi's ideas, and spin glass and turbulence. So this paper that it's referenced here is our paper, which is a paper on scientific reports showing the coexistence of turbulence, which is somewhat described here in this Hasselmann paper, one of the Nobel Prize on climate, and the Paris paper, which is on statistical physics. And our paper, our theory that we developed, connects those two papers. So we have experiments on this one, but we need to do optical experiments on these kind of things to, who knows, imitate or have an analogy with climate change or something related with all what we are suffering, and we can perhaps do it is in the lab to understand a little more. So we have a book on this subject, and also a paper on science and application, light science and application, reporting or reviewing all these things related to the Nobel Prize, which made us proud. But again, just to finalize, Nobel Prize in Physics in 23. Now, this has nothing to do with optical fiber, but it is to show how important is international collaboration. When this prize came this year for Pierre Agostini, Ferenc Krauss, and Annie Lullier, I wrote to Annie Lullier to congratulate her, and she replied and said, you were there at the beginning. What did she mean? She meant that at the beginning of all this that led to attosecond pulse, I was in France on a Brazil-France collaboration. We have two papers together. One is on the system, the laser system, and the other one is on this high-order multi-generation that was the base to generate attosecond pulse. All of this international collaboration and talks like this, conference like this, should stimulate students and professors to go around. And we have to take care of CO2, carbon footprint, and everything. But this interaction, it should go on, because we can then do things that we don't know are going to come. So to conclude, fiber lasers are fantastic tools. Raman fiber lasers can deliver very high power, can also be used as sensors. In the case of random fiber lasers, we can also, they perform as well as conventional laser. There are a lot of applications, but random soliton fiber lasers have not yet demonstrated. So there's something, and there are lots of things to do. And thank you very much.